Okay, good afternoon. We were talking about programmable logic devices. A programmable logic device, as I said, we have a device, an IC which is available in the market, manufactured, and then you can use it for different applications by programming it. We know all about programming because we do programming of microprocessors for different applications. We do programming of computers for different applications. So, it is not that elaborate. These programmable logic devices are simple ICs with some specific hardware inside, use it for limited purposes. Last class we talked about ROM, read only memories, which is a programmable logic device. What you have is, in a ROM, you have inputs, all the min terms are generated. There are n inputs, there will be 2 power n min terms, and then you have an OR gate array. These min terms are connected as required to get different outputs. For example, we said you have n inputs and m outputs. ROM, read only memory. As I said, there is no memory in that, like you have a memory in computer or microprocessor. It is memory because it retains whatever you do, program. But you can use it for different applications, same application different times. Even when the power is switched off, whatever you have stored, whatever you have programmed will remain. That is the reason why it is called memory. It is not a memory in the sense that you have in computers and all that. Now, this ROM has inputs, let us say n inputs, and these n inputs generate 2 power n min terms. So, what we have here is a decoder. What is a decoder? After all, it is our array of AND gates, different AND gates, and these min terms are given to a set of OR gates. So, this is AND array, OR array. So, whichever min term you want, supposing we have two outputs F1 and F2. F1 will have some of these min terms based on the truth table for a given application. F2 will have another set of min terms from the truth table. So, those min terms alone will be connected in the OR gate. So, that is what we marked like is cross last time. And OR gate may be, the second min term may have like that, so on. So, this is programmable, this is not programmable. When you have inputs, n inputs, 2 power n min terms are generated, just as in any decoder. But these decoded min terms can be connected as per your requirement in an OR gate. There are several OR gates, as many OR gates as there are output required. So, if this is m outputs, there will be m OR gates, and each of these outputs will have several of the min terms generated by this. This is, and how do you do this? We have a truth table, inputs and outputs, get the outputs, look at the min terms correspond to each output, connect them as inputs to the OR gate, and you get the output. So, the size of this ROM, as I said, is 2 power n Because there are n inputs, we have 2 power n minterms, and there are m outputs, so times m. This is bits. I told you the other day, you cannot do this, multiply this. For example, there are four inputs and 3 outputs. This 2 power 4 minterms times 3, this is the number of bits. So when you are asked for the size of the ROM, you should always mention as 2 power 4 times 3, not 2 power 4 is 16. 16 times 3, 48. This is not the way to say this. Because we don't know how many inputs are there, how many outputs are there. If you simply give the total number, you don't know how many inputs are there and how many outputs are there. So size of the ROM is always given as 2 raised to number of inputs times number of outputs. So generally it is 2 power n times m. We saw a few applications the other day. Now one problem with this ROM is used extensively where you want to store a truth table, for example, or some table like converter, code converter. Last time we saw an example of 7-segment display decoder. We also saw an example of converter from hexadecimal to ASCII. So these are standard circuits, standard applications, so you can get them done as ICs and they are available. If you are going to build a circuit involving using this hexadecimal to ASCII code, you get this, put it there. But sometimes when we do an application, when we do a design, we don't know. And also I said in the ROM, there are many types of ROM, maskable, mass programmed ROM or factory programmed ROM where you can program it at user programmed ROM, erasable ROM, EEPROM, ultraviolet erasable, electrically erasable, electrically alterable. These are the different types of ROM. There are technologies, I was not going to go into all this. There are some fuses which you connect, keep them connected to have a connection here. If you blow that fuse, the connection will not happen. That is the simplest technology. Later on today, the advances of technology, there are so many other techniques using the devices, charge current one direction, current in another direction, one particular type of charge, one other particular type of charge, all these things are used. This is beyond the scope of this lecture. You can, if you are interested, you can always go to any semiconductor device program course and read it. Now, the next one disadvantage of ROM is all the minterms have to be generated, will be generated, and only some of them will be used. This is a simple example. 4 inputs, 3 outputs. Not a big deal. Suppose I have a huge system with several inputs and several outputs. I may be generating a large number of minterms, but not all of them will be used. Only a few of them will be used in each of the outputs. So it's a wastage of hardware, wastage of semiconductor area. So can we now generate only those minterms which we need? So the next PLA, programmable logic device, we'll use will be called PLA or programmable logic array. Here also I have inputs and AND gates. And instead of producing all the minterms, I will only produce a few product terms which are required for my implementation, and then they go to the OR gate again. The only difference is if there are n inputs, earlier all the 2 power n minterms are produced, generated. Here I will not generate 2 power n minterms. I will produce a small number of not minterms but product terms, and those are required for implementing my final circuit OR, the OR gate. The advantage is this AND becomes smaller now, AND array becomes smaller. That way it has become more efficient. We will give a simple example. Suppose I have 4 functions f0, a bar, b bar, c bar, a bar, b bar plus a c bar, f1, a c bar, b, f2, a bar b, a bar b bar, b c bar, f3 would be b plus ac. I am going to generate 4 functions f1, f2, f3, f1, f0, f1, f2, f3 in 3 variables a, b, c. So, again I have here AND array whose inputs are a, b, c, and we will generate how many product terms are there here? A bar, b bar, is available here as well as here. B is here and here. AC is here as well as here. So, how many total product terms are required for this? 1, 2, this is already taken care of, 3, this is already taken care of, 4, this is already taken care of, 5. I need only 5 product terms in order to get all my functions f0, f1, f2, f3. Now, that means I will have here 5 outputs, not the minterms a bar, b bar, c bar, a bar, b bar, c, a bar, b, c bar, we do not have that now. Here it will be like that. Here this will be a bar, b bar, c bar, a bar, b bar, c, etc. Here it will be these 5, a bar, b bar, a c bar, b, b c bar, a c. So, I need AND gates, only 5 of them. Here how many AND gates are required? 2 power n AND gates are required, 2 raised to n. Here I need only 5, smaller number of AND gates can give me all the product terms I need, and I will combine them into OR gates as required earlier. F0, F1, F2, F3. F0 is a bar, b bar, a c bar. F2 is, F1 is a c bar, b. F2 is a bar, b bar, b c bar. F3 is B, BC bar. Where is AC? B plus AC. So OR gate requirement is same as the previous case. I will have as many output lines as required, and the OR gate will have inputs
Hello.
from these minterms as required. That part is common here. OR array is common, similar, not common, similar. AND array, instead of producing all the minterms possible and not connecting all of them, some of them will, very few of them will be used in each of the outputs. Out of 4 outputs, 1 or 2 or 3 product terms will be used, whereas I have so many product terms. Instead, I will only generate those product terms which are required. This is what is known as a programmable logic array. Here this is also, here this is fixed and is fixed. This is programmable. Why is it called fixed? Because all the minterms are generated, whether you want it or not. Whether you like it or not, all the minterms will be generated. Here, I can program this. And also this, both are programmable. So we draw what is known as a PAL table. The normal way of representing this problem would be, we will draw a table called PLA table, program logic array table. In the table we have what product terms which you need. What are the inputs available? What are the outputs required? Inputs are ABC. Outputs F0, F1, F2, F3. The product terms are A bar, B bar, AC bar, B, BC bar, AC. Now, A bar, B bar. So this will be, A will be 0, B will be 0, C is not there in the first product term. Second product term, A is 1, B is not there, C is 0. Third product term, this is not there, this is 1, this is not there. Second, this is B is 1, C is 0. A is 1, B is not there, C is 1. This is the input. What inputs are taken for each of these product terms, that is what this shows. This shows the different inputs of ABC required for each of these product terms. Output will be, we know, output will be F1 will be, F0 will be AB bar, these are not there. F1 will be AC bar, B, rest are not there. F2 would be A bar B, A bar B bar, BC bar, rest are not there. F3 would be B AC. Rest are not there. This is called the PLA table. From this you draw this, from this you draw this, and the whole thing is one IC. This is the PLA. Single IC will have all of this. So I need to program array. Given the inputs, earlier I said my size is 2 power n times m. Here I have to say how many inputs, how many outputs. That is not enough. If you simply say 3 inputs, 4 outputs, it is not enough. I will also say how many product terms are required. Product terms. So we give the size as 3 inputs, 4 outputs, 5 product terms. That is how I describe the size of this. So I describe this size of this. Okay. So generally we don't draw like this, we draw a little differently, because A bar, B bar, C bar are required. The circuit drawn is usual way of drawing this figure. A bar, B bar, C bar. My first minterm is, and this is first minterm is A bar, B bar, A bar, B bar, AC bar, A bar, B bar. My first minterm. This is put into an AND gate. These two inputs are provided AND gate to get my AB bar, A bar, B bar. Second is AC bar. Third is B. Fourth is A bar, B bar, already there, BC bar. Last is AC. This is my AND array, and this goes to F0 using an OR gate. We already said that this is these two, this is these two, third is this, and BC bar, fourth is B, AC. This is same as what I do, except that it makes it very clear that A, B, C and their inverts are used, A, B, C and their complements are used. We need 5 AND gates in which all these are combined like this. We have 4 OR gates in which it is all combined. This OR symbol represents this is an OR array, this AND symbol represents an AND array. As I said, this is the same thing, it is not new. What we drew earlier and this is not different, except that this is more elaborate. That is all. In the textbook you will see like this. We will have one more exercise on this. See, sometimes when you have multiple outputs, many outputs, usually the technique so far using corner map, simplify each output to the minimum possible way and draw circuits. Now, in the PLA case, we are going to have as few min terms as possible, as few product terms as possible. So, if there are 2 function outputs F1 and F2, if you draw corner maps, I may have one set of product terms for first map, another set of product terms for the second map, and I can represent number of min terms required, product terms required and choose a corresponding PLA. But on the other hand, if I draw F1 and F2, the 2 corner maps at the same time together, and if I can identify common min terms like here, I can reduce the number of product terms. When I reduce the number of product terms, anyway all the 3 inputs have to be given, all the inputs. The number of AND gates required will be smaller if the number of product terms is smaller. So, we will do an exercise of that type. I will give you an example of 3 functions. You can remove this also. Three functions. F1 is sigma m min terms 2, 3, 5, 7, 8, 9, 10, 11, 13, 15. F2 is sigma m 2, 3, 5, 6, 7, 10, 11, 14, 15. F3 is sigma m 6, 7, 8, 9, 13, 14, 15. I have 3 functions F1, F2, F3 defined by this. Now, we will draw the corner maps for each one of them. We will call them A, B, C, D. Now, this should be 0, 1, 2, 3,
சரி ஏன் என்னாச்சு ஏன் இப்படி
4,
ப்ராப்ளம்
5,
தெரியலையே ஆனா அவர் பேசுறது எனக்கு கேட்க மாட்டேங்குதுடா
6, 7, 8, 9, 10, 11, 12, 13, 14, 15. F2, this is F1. F2, this will be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. F2. F3 would be 6, 7, 0, 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So, these are three corner maps. I want to simplify them. If I do not have this common product term like this, earlier we had 5 product terms which covered all the outputs, some of them were repeated. F1, F2, F3, F4, F0, F1, F2, F3, we had common product terms which we were able to use because we had to generate these product terms and use it in more than one output. If I do not consider that way, if I only look at these as individual corner maps, I will do it in the simplest possible way. This should be 1, this will be another, and this will be third. I will write it as without considering common min-term product terms between functions. Without considering common product terms between functions, this will be the optimum way of doing it. This is A B bar, this is C B D, this is B bar C. Is it right? AB bar, what is that? AB bar I have done this way. AB bar CD BD. BD is fine. CD would be this. AB bar CD BD. AB bar BD. This is BD. BD. This is B bar C. I have it differently here, that doesn't matter. AB AB bar CD would be, I consider this as CD and BD. Anyway, doesn't matter. Now, this one, this will be this one and this. This will be, F2 would be, this is C or A bar B D. The last one would be, this will be this one, this will be this, so this should be F3 would be B C or A B D or A B bar C bar. Now we have three minterms here, two minterms, three minterms. So this will require an AND gate, another OR gate. This is one AND gate and one OR gate. This is again three AND gate and one OR gate. A number of inputs also large. Instead, now what I am going to do is look at the map simultaneously. Look at the map simultaneously and simplify it such that we have common minterms between the two or three. If we have a common minterm between this and this, even though it is not the best way to simplify the map, I will use it because when I am going to use a PLA, I would like to have as few minterms as possible. So that way if you look, you have this between this and this, I will do a different color chalk. This I cannot simplify it, I can use it as it is. I am not going to do anything to this because it is already the simplest form, this and this. Whereas here what I am going to do is, I am going to keep this and do this as one. Instead of connecting all the four ones, instead of grouping all the four ones, I am going to group these two ones because these two ones are already grouped and this. So these two have common min term, product term. If I can, instead of this 4 together, if I only do this and do this, I have this and this common. Likewise, these 4, these 2 I can have as common to this, these 2. So, this and this are common, this and this are common. So, if I use this here, I do not have to use it again here, and this and this. Okay. So, now I have here some terms which are common, so it is going to be different. I am going to now rewrite the F1 as BC bar A B bar C bar A B D A bar B D A B D. Now, what is A B D? This is A B D. This is A B D. A bar B D, this is 1. So, this is taken care of, this is taken care of. A bar B C, A B bar C bar is this, and B C bar is the whole thing. B C bar is this and this. B bar C rather, B bar C. So, these 4 as one min term, one prime implicant. This is one prime implicant. So, I have now this was 3 here, I have made it 4. Looks like it is more, but not. It is, later on I am going to combine this to the other one, so that some of them will be common. So, total number of product terms will be less in this case. Then the next one will be same, I am not going to change it. F2 is same as this, because it is already the minimum possible. F2 is minimum possible. So, C. Third one is this. Since I have now combined this and this, and this and this, I am going to have some common terms here. This is going to be ABD was originally there, ABD, this is ABD, ABD, F3 is ABD, this one is AB bar, C bar, and this is BC. Now, if you look at this, let us see if there are any common terms now. A, B bar, C bar, this is common. So, we have a common min term, common product term between 1 and 3. Then A bar B D, second product term which is common. ABD, So, 3 sets of min terms, product terms are common between these 3 functions. So, I will now have 3 less product terms to be generated. Here it is how much? How many? 1, 2, 3, 4. Here it is 1, 2, 3, 4, 5, 6, 7, 8. We need only 8 gates. On the other hand, here you have to come back, count also the OR gates. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is 10 AND gates. Total of 10 gates here, whereas total of 8 gates here. Total number of inputs also if you count, this comes as 25, this comes as 22. This is 10 gates, 25 inputs. This is 8 gates, 22 inputs. Even though it looks like I have expanded it unnecessarily, including one extra term, this has become now better. So, now I can draw the PLA table. What are the inputs? How do you draw the PLA table for this? We draw what product terms are used, what inputs are used and what outputs are there. For this problem, PLA table is product terms, inputs are A, B, C, D, small a, b. Outputs are F1, F2, F3. Product term, first product term is A bar BD, A bar BD. Second product term is ABD. Third product term is AB bar C. AB bar C bar. Fourth product term is B bar C. Then C, BC. F1 has this. These are not there. F2 has this and C. F3 has this is how you draw a PLA. This is how you design a PLA circuit. PLA circuit, the simplification of the logic function using corner map, you have to take some extra steps to minimize the number of product terms required totally. Whereas in single design, we have so far seen, we would optimize the number of product terms by combining the ones in the most efficient way. If you can do it, fine, then there will be F1, F2, F3 as I had done here. But if you do this, I can reduce the number of product terms, thereby making the size smaller. So, what is the size of this? As I said, size, you do not simply say input time output. The size is now, you have to also include the number of product terms. size is input 4 outputs 3 product terms. How many? 1, 2, 3, 4, 5, 6. So when you're going to buy in the market a PLA to implement this function, you should have 4 inputs, 3 outputs and product terms 6. It is not always possible to get what you want. You can get the next higher size available. You can't have odd number of inputs, odd number of outputs, odd number of product terms. Every possible combination that you want may not be available commercially. In which case what you do is to choose the next higher size and then implement it. So after this I am not going to draw that AND array or array. So this will be the, you complete this map, A bar, B bar, C bar, D bar, all these product terms, 5, 6, 6. Using AND gates. All these are written here, A bar, BD, etc. And then combine them into 3 outputs using OR gates. F1, F2, F3. This is the total design. So now we have we started discussing programmable logic devices, saying that these are simple hardware which can be used for many applications by programming not in the sense of programming C language or programming computer or microprocessor. This is programming in the sense I can change the configuration a little bit to get different applications. The first of the programmable logic devices we saw was ROM, where we have a series of inputs producing all the possible minterms, combine them in different OR gates to get the outputs. The problem with that is we have too many minterms, minterms, many of them may not be used very much, once or twice, especially when the large number of inputs and outputs are there. The size will be huge, but I may be using only a small part of it. So we go for programmable logic array, where we write the functions, simplify it, make as many product terms as possible as common, and only generate those product terms using AND gates, and then combine them with OR gates. In this case, this is programmable AND gates, programmable OR gates. In the case of ROM, it is fixed AND gates because the decoder gives you all the possible minterms, but fixed programmable OR gates. One more variation of this is called programmable array logic, different from programmable logic array. This is good, this programmable logic array, except that we have to do all this programming, find out the common minterms, etc., etc. The programmable array logic, one is PLA, the other is PAL. PIL, in which we will have a programmable AND array as we defined earlier. That means you can have inputs, of course with inverters and all that. I am not showing all that. And generate product terms as required, like earlier case, using AND gates. So we will have product terms P0, P1, P2, etc. And then this is going to an OR gate array again as before, but the OR gate inputs are fixed now. So there are, let us say, two OR gates, two outputs, F1 and F2. Prior hand will say F1 can only take P0 and P1, or F2 can only take P2 whatever. So this in this case is fixed. So OR is fixed and is programmable. So now we have ROM and OR and is fixed programmable. PLA, both are programmable. PIL, this is programmable, this is fixed. That is the difference between the three types. So how will you use this? We will have a simple example. It's the same. Again I have to write the corner map, simplify it, get the midterm product terms, but then we have to keep in mind only a few product terms is available or available for each output. That is where the problem is. Now I will give you an example. Supposing I want to generate a full adder, 1-bit full adder using PAL. Use PAL to design a 1-bit full adder. So we have inputs A, B and X, Y or whatever, X, Y, C in, these are inputs, outputs, sum and carry out. We have seen this before, we have seen how to design this, we have seen multi-bit adders, we have seen how to use adder subtractor, we have seen how to improve the speed by CLA, carry lookup adder. We also seen BCD adders. Now, in this case we are going to use the simple adder. So I have 3 inputs. X X bar Y Y bar Cn Cn bar. So all the three inputs and their complements are available. So this is X X bar Y Y bar Cn Cn bar. Now I have two OR gates. This PIL consists of two OR gates with. Now I have to specify. In this case, earlier I said for PLA you need to specify input, output, and number of product terms. Here I have to specify number of inputs, number of outputs, and how many inputs can go into each of the OR gates. In this case, let us say two OR gates. So here I have three inputs, two outputs, that is sum and carry, and four inputs in each OR gate. So I have here these are fixed 1, 2, 3, 4 OR gates, 4 inputs into one OR gate, and again another OR gate with 4 inputs. This is pre-defined. Yeah. I have to use one for sum, other for carry out. This is fixed, but then what is not fixed is which of these terms go into this AND gates. For example, if you write the sum truth table, sum expression, this x bar, y bar, C in x bar y, C in bar, xy, xy bar, C in bar, xy, C in. Carry is x C in plus y C in plus xy. Now, first is 4 terms, x bar, y bar, C in, x bar, y bar, I'm sorry, x bar, y bar, C in, x bar, y, C in bar, x, y bar, C in bar, x, y, C in bar. So I program this OR gate with 4 inputs is given, you cannot change it, but what are these 4 inputs? What product terms? These are AND gate. So what of these, which of these input x bar, y bar, c in bar will go into each of these, we can decide. That is the programmable part of it. For this it is x c in, x c in, y c in, xy. But this is not going to be used. So we are not going to this AND gate, each is an AND gate. This AND gate I will not use. Only 3 AND gates are required, 3 inputs. Out of 4 inputs available, I will use only 3 inputs. This is called programmable array logic. So, we have now seen different types of programmable logic devices. ROM, which is programmable OR gates, and is fixed 2 power n if n is the number of inputs. We have programmable logic array, where we have a programmable AND array, or to give many product terms that we want and combine them in OR gates, again programmable. That is to simplify the number of inputs that is required, rather than a ROM in which all the inputs are available to you whether you use it or not. One step further, you can go and say I have these OR gates, you can only take 2 inputs, 3 inputs, 4 inputs, and you have to generate the product terms such that your function falls within this. In other words, after looking at this, you will have to choose, I want 3 input, 2 output, and OR gate each will have 4, because there are 4 inputs here, there are 4 terms here, at least 4 inputs for each OR gate. That is how you do it. So, this completes the programmable logic devices, and also called combinational logic. We will start with a new topic, new, not only new topic, it is a change from whatever we have seen. We are going to another part of the digital system design in the next lecture. Are there any questions in everything I said today? Because I did a lot of examples. I gave you examples of PAL, PLA, how to optimize it. We did 2 examples and also told you how to draw this. That is how we will find in the book. So, we also did PIL, give an example of full adder, 1 bit. ROM, of course, we saw last time, examples. So, all these 3 form part of programmable logic devices. There are also lots of programmable logic devices other than this. At this point, we will stop here and we will proceed to another area. Any questions?
ROM is used in computer. ROM is used in computer.
Yeah,
Used
ROM
in
is,
computer.
yeah, ROM is used. Yeah, ROM is used in computer. ROM is also used for other devices like
This kind of ROM is used
yeah, yeah.
or latch like
No, latch is a RAM. Latch is not a ROM.
RAM. Yes.
We will talk about
Okay.
it. But what is ROM? As I said, ROM is nothing but a hardware. You have a truth table, and you have to have several inputs and several outputs, and you store that and use it. It can be for any simple design that we saw the other day. Even the full adder, for example, you can do it. But the problem is, when you use it in computer, it is used only for certain specific things. You want to store the hexadecimal to, you see, we did an example of hexadecimal to ASCII code conversion. So, when you have an input in hexadecimal and you want to convert it to ASCII, you can use a ROM which is part of the computer. So, ROM in computer will store things which are required like tables, sign value of different angles. It is not going to change. You have to decide what is the resolution you want. Supposing you want every degree, sign value from 0 to 90 or 0 to 180. 0 degrees, 1 degree, 2 degree, 90, 91 like that up to 180. Then you know the values in advance, you can calculate them and store them. So, whenever you say sign, for example, calculator, you take the calculator, when you punch in sign, you give a number and sign, it does not do a calculation, it takes it from this ROM. It is stored in the ROM. It takes it from the ROM and uses it. That is what I said, it is storage in the sense, it is a memory in the sense, whatever you put remains. it is not, it does not disappear when you switch off the power. Because of the technology, as I said, there is fuses, the fuses can be blown, you can retain the fuse if you want a connection, if you do not want the connection, retain the fuse, do not want the connection, remove the fuse, all that are, that is the earliest technology, mass programmable. Or today you can do electrically, change a charge can be changed. For one type of charge you have connection, the other type of charge you do not have connection. So all these are done, but there is no going back on it. I can erase the whole thing, erasable ROM, it is a programmable ROM, I can erase it, I can reprogram it, all that is possible. I can do erase it using ultraviolet rays, I can erase it using electrical pulses. But once you do, it remains. It is called non-volatile. I am going to come back to memory later on. This is not a memory discussion. What is a non-volatile? It does not disappear, it remains even after power is gone. We are going to later on come into memory discussion where we have RAM, we are talking about read, write, latch, somebody said latch, all those things will come later on. At that time these are called volatile memories. If you remove the power, whatever is stored will go. So computer use ROM, but for different purposes, not for memory that you use in your computer. You have RAM, lots of memory. They say, for example, you have 1 GB memory in your computer. This is a volatile memory. You can put things, use it. Supposing you want to run a program, what do? You first, you have a CD or it is stored in the computer somewhere, you get it in a pen drive or whatever, get it onto this RAM, run the program, at the end of it goes away. Word processing, you have to store it. When you want to work on it, you put it into this RAM, change it, and then it will can save it. This ROM, that way ROM is also used in computer in the sense to store tables, converters, whatever you want to store. That is another application. I am not talking about that application today. ROM and RAM in computers have different purposes. But here I am using ROM as a programmable device. Instead of doing gates and multiplexers and all that, which is fixed, now I have one application in which I can change things. There is a device here to me. The device, for example, adder, full adder. You have to buy a full adder. But here I can use a programmable logic array, programmable array logic to design a full adder. That is what I mean by programmable. It is programmable as different uses. That is all. There is a difference here. So it is a programmable device, ROM, PLA, PAL, and different applications for a given hardware. You can change a content, use it. That is all. Any other question? No question.
Sir, programmable logic करें.
Huh?
Programmable logic करें. And it is programmable.
What?
Programmable logic करें. And under is programmable. It's correct. But on that I give the input and output table, PLA table.
Yeah.
A B days given. A is 1, B days is 0. C output is days. Days means that's don't care condition on.
Yeah, that is not
don't
there.
Care like one.
That is not don't care. That input is not there. You see, the input can be, see we have A, B, C, 3 inputs. A can be 0 or 1, B can be 0 or 1, C is not involved in that gate. C does not go into that gate. When you put a dash there, it means that input is not there. That is all. It is not don't care. There are 3 inputs. I say there is an OR gate, AND gate. The AND gate output is a product term where the inputs are A, B, C, D. A may be complement, so you put 0 there. Whenever there is a bar, you put a 0. It is only a table, just for our understanding. B can be 1 or 0, so I put a 1 or a 0 if it is B or B dash. C is not into that. My product term is only A B bar, let us say. C is not used, so I will put A 1, B 0. That is for our understanding, so that you can program it properly. That is all. Just because you put 0 or 1 in your notebook does not mean anything. It's only for our understanding. Okay?
Okay.
And a
Okay, sir.
dash means it is not there, that input is not there. Okay, any other question? No more questions? Aruna usually ask questions, today they don't have. Okay, if you don't have any questions, we'll stop now and see you next Monday. Have a good evening.
In PLA, why we are using only AND gates, sir? There is no, why we are only AND gates?
What do you mean by that? We are
In
using AND and
AND
OR
gate,
in all the 3.
yes, sir.
RAM, PAL, PLA we use, and all the 3 we use AND gates and OR gates. Where you only
Yes,
AND
sir.
gate
Why,
you are.
sir?
What do
Why,
you mean?
sir?
Why? This is how it is done. This is how it is designed. Why means what? I don't understand your question, because
Why we are not using AND gates, sir?
that way. Okay. No problem. But you can use NAND gate and put a inverter. No problem. It is possible. But generally it is not. It is only an explanation of how it is done. Actual design may be a NAND gate and an inverter, which is also an AND gate. A NAND gate can be used as an inverter, you know that. Yeah, that is a manufacturing point. Conceptually, we have AND and OR because all our logic design, all this corner map simplification, implementation, all that we have seen AND OR and inverter, right? AND OR invert. After doing it, we can convert it into NOR gate only, NAR gate only, and all that. So that is the standard form is to write AND is a product term, and all these product terms go together an OR gate, and there are inverters wherever required. That is why this form has been chosen for teaching. I am not saying NAND gate cannot be used. It can be used. That way
Sir,
we
but
have.
there is a,
Say it again.
but, but there is difference between the uses, sir.
No.
If use AND gate means there is difference.
No. You have to understand it very clearly. The function is given.
இந்த அப்படி நிக்கிறது.
The function can be implemented using AND OR invert, or I can use OR AND and invert. I can have all OR gates followed by an AND gate, or I can use NAND gates, and I can use NOR gates. How you do it is not important. The conceptually this is how it works. If you are, yes, you can also manufacture a product PAL or PROM using NAND gates. So whenever there is an AND gate, you know how to get an AND gate out of NAND gate. Use a NAND, put an inverter. That's all. Conceptually, nothing changes. What you are saying is an implementation detail. That is all. That doesn't change. You are saying it will change. No, it won't. You have to stick to this. F1, F2, F3, wherever I have designed, derived, cannot change because you use NAND gate. You cannot change that. Then it doesn't work. You have a circuit, you have a problem given to you, you draw the truth table and you get the logic functions and implement it. How can it change? I can use an AND gate, OR gate, inverter, or I can use a NAND gate, use an inverter or the output of each AND gate, and it's also fine. There's an implementation detail. Okay?
Okay, thank you, sir.
Thank you. Okay. Okay, then I will sign off today. We'll see you Monday.